Hello, this is Formal Lab number 2 by Harman Singh, Audrey Downs, and Megan Deming. The question we've been investigating in this lab is how does the viscosity of the fluid affect the forces acting upon the ball bearing as it drops? Our hypothesis is that the corn syrup will have a higher resistive force than water, and water will have a higher resistive force than the isopropyl alcohol. The independent variable used was the fluid the ball was dropped into, and the dependent variable was the resistive force of the fluid that was found. We set this up by dropping a metal ball bearing through 3 different graduated cylinders with corn syrup, water, and isopropyl alcohol. And the goal was to find the resistive force of these 3 fluids and compare it to what we can find online in different studies that have been done. Our main findings were that the mu of corn syrup was very high, the mu of the water was much lower, and the mu of the isopropyl alcohol was similar to that of water but still significantly lower. On the left, we have a force diagram showing the viscous force acting on the ball as well as the force of gravity acting on the ball in the downward direction. On the top right, you can see our system schema, which has the ball bearing circled to show that it is the main focus of our trials. On the bottom right, you have the energy pie charts, which show the change of the potential energy of the ball bearing to eventually kinetic and internal energy. This will vary a little bit for each trial, but here's a general model. This lab was set up by filling 3 different graduated cylinders with water, isopropyl alcohol, and corn syrup. The tracker app was used to record each of these trials, and then after the ball bearing was recorded dropping into each solution, we then analyzed it using the tracker app. Here you can see the velocity versus acceleration graphs for each trial. This shows that since these are linear, there is no drag in these trials, and we will be omitting it from the rest of the lab. Here you can see the velocity versus time and acceleration versus time graphs of the water trials. To find the viscous constant of water, we set F net equal to the negative force of gravity minus the force of drag plus the force of viscosity. F net is equal to mass times acceleration, and we use the acceleration to the right when the ball is in the liquid and moving. The force of gravity is equal to mass times acceleration, and the force of viscous is equal to 6 pi times the viscous constant times the radius of the ball, times velocity, which is also to the right, and we use the corresponding velocity, which was at 0.112 seconds. We solved for the viscous constant and found it to equal negative 5.4617. The negative here is directional and can be ignored later when comparing values. Here you can see the isopropyl alcohol velocity versus time graph and the acceleration versus time graph. The same math was used to find the viscous constant of isopropyl alcohol as was for water, and we found it to be negative 2.5929 Newton seconds per meter squared. As shown by the blue dot, corresponding accelerations and velocities were used for these calculations as the ball was not able to reach its terminal velocity during these trials. The corn syrup trial data showed an average acceleration of 0, which means that there is a no net force acting on the ball and that it has reached its terminal velocity. The same process as before was used to find the mu, and it was found to be negative 8,871.9739, which is obviously inaccurate, but we will discuss this later. However, the takeaway is that this number is very large, which means it has a very large resistive force acting upon the ball. On this slide, you can see the viscosities that we have found through our trials compared to the actual viscosities. Water, we found it to be 5.4 Newton seconds per meter, and the actual is 8.9 times 10 to the negative 4 Newton seconds per meter squared. The isopropyl alcohol, we found it to be 2.59 Newton seconds per meter squared, and it's actually 2.1 times 10 to the negative third Newton seconds per meter squared. The corn syrup, we found it to be 8,871 Newton seconds per meter squared, when it was actually found to be between 2 and 3 Newton seconds per meter squared. This leads us to many sources of error and limitations while conducting this experiment. The sources of error we found in this experiment were that the tracker app is very limited to the estimates of the position due to poor quality of video, and the graduated cylinders for isopropyl alcohol and water were not long enough or full enough to get the metal ball to fall at its true terminal velocity. Thanks for listening. Have a great rest of your day.